In this video I will do close to 10 examples on one sample test. You may recall that we did, I did an earlier video on one sample test. So these are examples on those. So let's start with the first example. Example 1. Suppose you have a random sample from a normal population with mean mu and variance sigma square. Assume sigma square is known, right? And consider testing the hypothesis that that mu equal to mu 0 versus the alternative hypothesis that mu is greater than mu 0, and with H0 rejected, if root of n times x bar minus mu 0 divided by sigma is greater than the percentile of the standard normal at 1 minus of O. And the question is to find beta. Remember, beta is the type 2 error probability. Okay, so beta by definition is the probability of type 2 error, right, which is defined as the probability that we accept H0 given that H1 is true. Now in this case, this is the rule for rejecting the null hypothesis. So so we will accept the null hypothesis if okay, and H1 is true if mu is greater than mu 0. If you look over here, this is H1, right? When mu is greater than mu 0. So the question is how to calculate this probability. Now I will show you how. I'm going to write this as right? You see why I'm doing this in a minute. And now I'm going to group these terms like this: x bar minus mu in one term and mu minus mu 0 in another term. And then I'm going to I'm going to take the second term to the right hand side. So now we know, I don't know whether you guys remember from the video I did on normal distribution, one of the properties I gave you is the following, that if you have a random sample, you see we are assuming that this is a random sample from this. Now, if you have a random sample from a normal population, then X bar also has the normal distribution with these parameters. This is one of the properties I talked about in the video on the normal distribution. Now, if X bar has this, then root of n times sigma times X bar minus mu must have the standard normal distribution. I mean, it's easy to see that. You should take away mu on both sides, this will go to 0, and then you should multiply by this constant, the variance will become 1. Alright, so let me put this in a box, if you don't mind. Alright, so what I have shown here is that this must have the standard normal. So we can replace over here the probability that okay. All right. So now remember, I removed the conditioning from this line to this line. I have removed the conditioning because of the fact the condition on the true population mean mu being greater than mu 0, this has a standard normal distribution. So we have made use of the conditioning. All right. So hence it's not needed anymore, right? Because condition on this fact, the argument here is that condition on this fact, this has a standard normal. So we have made use of it. Alright, and finally you can write this as capital Phi. Remember, capital Phi denotes the CDF of a standard normal. So this is the answer. This gives the answer to the question that find beta, right? So that's example 1. The next example I'm going to do is the following. Example 2 is same as example 1, but reject H0 if right? Reject H0 if x1 is just the first data point minus mu0 divided by sigma is greater than this, right? And the question is the same, that is to find beta. So let's start with the definition that beta is the probability of type 2 error, okay, which is probability that we accept H0 when H1 is true. Okay. And which is the probability that, right, this is the rule for rejecting H0. So the probability for accepting H0 is this one. Given that mu is greater than mu0. Okay. Now I'm going to do the same thing as I did in the previous example. So I'm going to subtract a mu and add a mu. Right, now I'm going to put brackets around this. I'm going to take the second term, which is this one, to the right hand side, as I did in the previous example. Now, based on this conditioning, we know that x1 has a normal distribution with parameters mu and varying sigma squared, right? So x1 minus mu divided by sigma will have, condition on this, will have the standard normal distribution. Yeah? Because if x1 is normal with mu and sigma squared, x1 minus mu will be normal with 0 mean and varying sigma squared, and divided by sigma will be this. Right? And this. So once again, I removed the conditioning from this step to this step because I made use of this fact that condition on mu, this has the standard normal. Mu divided by sigma. Alright, so this completes example 2, right? And the next example is example 3. So this is same, once again, this is the same as example 1, except the rejection rule is the following. That is, you choose a number I, which is an integer between 0 and 99, and you reject the null hypothesis if it falls between 0 and 4. Alright, so let's start again. Beta is the probability of type type 2 error. So this is the probability of accepting H0 when H1 is true. Now accept is the opposite of rejecting, so you can write this as 1 minus the probability of rejecting H0 when H1 is true. Okay. Now this is the same as saying that this is 1 minus the probability. We reject when I is between 0 and 4. When mu is greater than mu 0. Right, now this is where the answer comes in. Now remember, I is the number between 0 and 99, and there are 100 numbers between 0 and 99, and between 0 and 4 there are 5 numbers, 5, 0, 1, 2, 3, 4, 5 numbers. So the probability of this, because I is not related to mu, right? So you can pretty much ignore this. So basically you're looking for the probability that I is between 0 and 4 inclusive, which is 5 out of 100. Because there are 100 numbers between 0 and 99, and there are 5 numbers between 0 and 4. Okay. So the answer is 0.95. So this completes example 3, right? Next example, example 4. The bag contains 20 balls. Okay. Let P denote the probability denote the probability that a ball that you choose from the bag is defective, right? Right? So basically you have 20 balls in a bag and you're choosing one at a time, right? And let P denote the probability that a chosen ball is defective. And let Y denote the observed number of defective balls. So you're choosing one ball at a time, and Y denotes how many of the balls turned out to be defective, right? And we want to test the null hypothesis that P is equal to 0.2 versus the alternative that P is not equal to 0.2. And suppose we reject the null hypothesis if y is greater than or equal to 7 or less than or equal to 1. The question is to find beta. Alright? So beta, once again, is the probability of type 2 error. Alright? And this is the probability that we accept H0 given H1 is true. Right, now remember, accept is the opposite of rejecting. Right, so we reject if it's greater than or equal to 7 or less than or equal to 1. So that means we accept if the opposite of this is true, which is y between 2 and 6, and H1 is true if p is not equal to 0.2. Now remember, y is a discrete random variable. It can only take integer values. So when y is between 2 and 6, it can only take 2, 3, 4, 5 or 6. So you can write this as the sum Now, y denotes the number of defectives in a bag of 20. So what distribution will it have? P is the proportion, is the probability that a ball is defective, and y denotes the number that are defective. So clearly, from your probability 1 course last semester, you should know that y must have a binomial distribution with parameters 20 and p. So this is the answer to example 4. Alright, so it's just the final step is the crucial step, because I'm using the fact that y has a binomial distribution with parameters 20 and p. Alright, the next example is example 5. Suppose you have a random sample from a normal population with mean mu and variance equal to 4. Consider testing the hypothesis that mu equal to 0 versus the alternative that mu equal to 4. And reject the null hypothesis H0 if the following is true. Okay, the question is to find beta. So this is similar to one of the previous examples I did. So beta is type 2 error, which is the probability of except H0 when H1 is true. Alright, so now except is the opposite of rejecting. So this is the same as root of n times x bar divided by 2 given H1 is true if mu equal to 4. Okay. Now here I'm going to do a standardization, a trick that I used previously. Now I'm going to, because the true population mean is 4, right, I'm going to do this. Okay. Now put this around, okay, and I'm going to take the second term that's outside the brackets to the right hand side, so you will get this. Right, now conditional on the fact that mu equal to 4, this must have a standard normal distribution because of the same argument that I used previously, guys. Because x bar is normal, right, with mean 4 and variance sigma squared over n, right? So you should do this, you should follow the standardization. And let me just explain. X bar, given mu equal to 4, x bar is normal with mean 4 and variance sigma squared by n, right, which implies that x bar minus 4 is normal with mean 0 and variance this. Which implies that you should multiply by this, right? This will have a standard normal, right? Okay, so this is what I meant earlier also, that condition on this fact, right? That this is a standard normal. Alright, so this is the probability that a standard normal variable is less than or equal to this, right? Now I have removed the conditioning one again because I have used this conditioning to argue that this is standard normal, right? So finally this is phi is the CDF of standard normal at okay. So this completes example 5. The next example is example 6. Suppose consider testing consider testing this versus this with alpha equal to 0.5. Remember, alpha is the probability of type 1 error, also known as the significance level of a test. If this is a different kind of question, right? So if you require that with probability at least 0.9, the standard test will reject at 0, when in fact mu equal to 95, how large should n be? Now, when I say standard test here, I mean the test that I referred to on the video on one sample test. So you will need to go back to that video and see what is the standard test corresponding to this versus this, right? I will write it down in a minute. Okay, so what the question is asking you is, we want the probability of rejecting at 0 using the standard test when the population mean is 95, right, to be at least 0.9, in other words, greater than or equal to 0.9. So given this fact, what should n be? That is the question. Right, now according to the standard test, so you'll have to look back on the video on one sample tests. So if you look at that video, right, you will see that the standard test will reject the null hypothesis for this, right, if the following is true. Root of n divided by sigma. Sigma is the root of the sigma squared, which is root of 20, right, times x bar minus 100. 100 is the value for mu specified under the null hypothesis, right, is less than minus z 0.05. This is the alpha, sorry, 0.95, This is 1 minus alpha. Alpha is given to us as 0.05, so 1 minus alpha is 0.95, right? So this is the standard test for rejecting the null hypothesis, given that mu is equal to 95, and we want this probability to be at least 0.9. Okay. Now we need to solve this inequality for n. N is a sample size, right? So I'll show you how to do it now. The first thing I'm going to do is because we are conditioning on the fact that the true population mean is 95, I'm going to do the following trick, which I did already before. Okay, this is what you get. Okay. Now I'm going to group this as I did before, and I'm going to take the second term, this one, to the right hand side, right? So if you do that, you will get the following. The probability that right? Okay, now condition on the true population mean equal to 95. The distribution of this is standard normal. It's not difficult to see. Once again, I will explain if you want me to. I mean, X bar from the previous video, on the video on this normal distribution, you will see that X bar condition on this has this normal distribution with the true population mean 95 and variance sigma squared by n, which is 20 divided by n, right? Which implies that if you subtract 95 on both sides, right, then this will be 0 normal with 0 and variance this, right? And now if you multiply both sides by this, you get the standard normal, right? So that's what I'm going to use now in the next line. In the next step, I'm going to use this result, that condition on mu equal to 95, this guy has the standard normal distribution, right? So you get the probability that NO1 is less than or equal to 5, yeah, is greater than or equal to 0.9. Once again, I remove the conditioning from this line to this line because I use this conditioning to argue that this has a standard normal. So we don't need this conditioning anymore, right? Okay, so let's continue. So in the next line, I'm gonna the probability that the phi, remember phi is the standard, is the notation for the CDF of standard normal. So this is same as phi at yeah, okay. You with me, guys? Okay, so, and in the next line, I'm going to take the inverse function of phi both sides. Because this is an increasing function, because phi is an increasing function of its argument, we can say that this is okay. You can say this is the case. right? And then in the next line, I'm going to take this constant to this side, right? So this is going to be root of n greater than or equal to yeah, and we are nearly there. So in the final step, I will just square. So if you square this, you get n, and if you square this, you get 20 divided by square of 5 is 25. So that completes example 6, which is a bit different from the previous example. But it's not, I mean, once you do a few examples like this, you should get used to this, right? The next example is example 7. Example 7. Now, consider so here we are testing for the population standard deviation sigma equal to 10 to the power minus 2 versus greater than 10 to the power minus 2. Alpha is the probability of type 2 error, 0.05. Sample size is 35. Question is to find beta. So to find beta, I'm going to use the standard test. When I say standard test, I mean the test I gave you in the video on one sample tests. Right? That's what I mean by standard tests. So this is now, if you look at the video I mentioned just a second ago, you will see that the rule for accepting the null hypothesis is n minus 1, which is 35 minus 1 times s squared, the sample variance, divided by sigma squared, which is this, less than or equal to chi squared with n minus 1 degree of freedom, which is 35 minus 1, and 1 minus alpha, which is 1 minus 0.05, given that sigma is greater than, right? This is H1. Right now, I'm going to do some simplification here. Sorry, I'm going to 35 minus 1 is 34. So I'm going to write it as 34 times s squared. Now, because the true population standard deviation sigma is no longer equal to this, is a number that is greater than 10 to the power minus 2. I'm going to do the following. I'm going you'll see in a minute why I'm doing this, but this guy here, you should look at one of the properties of a chi-square distribution that I talked about on the video on chi-square distribution, that this, given that the true population standard deviation is sigma, this must have a chi-square distribution with n-1 degree of freedom. But before I get to that, let me take this guy here to the right hand side. Okay. Okay, now in this line I'm going to use the fact that this, once again please look at the video on chi-square distribution. You will see that one of the properties I mentioned over there is that n-1 times s squared divided by sigma squared must have a chi-square distribution, must have a chi-square distribution with n-1 degree of freedom, which in this case is 34. So once again, I don't need this conditioning anymore, because I use this conditioning to argue that this has the chi-squared with 34 degree of freedom. Alright, so you can write this, if you like, as capital F So here, this notation denotes, so F denotes the CDF of a chi-square variable with 34 degree of freedom. Right, so that completes example 7. The next example I'm going to do is example 8. Suppose you have a variable x that has the geometric distribution with parameter p. Consider testing the hypothesis that the null hypothesis is where p is 0.1 versus the alternative hypothesis that p equal to 0.2. And suppose we reject h0 if x is less than or equal to 5. The question is to find alpha and beta. Right. Remember, alpha is the probability of type 1 error, and beta is the probability of type 2 error. So let's first find alpha. Which is the probability of that you reject h0 when h0 is H0 is true if P is 0.1. Okay. Now remember, for a geometric variable, if x is less than or equal to 5, then you can take the values 5, 4, 3, 2, and or 1. Alright, so so this is equal to, this is the probability mass function of a geometric variable, which I'm sure you know is P times 1 minus P to the power I minus 1. Alright, now if you have a calculator you can simplify this, so I will leave it like this for the moment. Right, now the second thing we want to find is the probability of type 2 error. Right, which is the probability that we accept H0. Right, we accept H0 when H1 is true. Right. So this you can write as, we reject if x is less than or equal to 5, so we accept x is greater than 5 when p is 0.2. Okay. Now by the opposite of x greater than 5 is x is less than or equal to 5. So you can write this as 1 minus the probability that x less than or equal to 5 given b 0.2. Now if x is less than or equal to 5, then you can take values between 1 and 5. Excuse me. So this is the probability mass function of a geometric with p equal to 0.2. So it's p times 1 minus p to the power I minus 1. Alright, so this completes example 8. The final example is example 9. Example 9. Consider testing the null hypothesis that the population mean is equal to this versus the alternative that mu is equal to mu1, which is less than mu0. Okay. And assume that the population variance is known, right? Assume sigma or sigma squared is known. Let alpha denote the probability of type 1 error. I mean, you guys know this anyway. This is the definition of alpha, and the beta denotes the probability of type 2 error. Right. The question is to show that n is the sample size, is equal to the following. Okay, so this is a slightly different question to the kind that we have seen. Right. So to do this, right, you start with beta. Remember, beta is the probability of type 2. Type 2 error, right? Which is the probability that we accept H0 when H1 is true. Right, which is, now I'm going to use the standard test. When I say standard test, I mean the standard test for testing this versus this when sigma squared is known. Now if you look at the video I did previously on one sample test, you will know what the standard test is, right? So according to the standard test, the rule for accepting H0 is this. And H1 is that mu is equal to mu1. Okay. Now, I'm going to use the same trick. Because the true population mean is mu1 and not mu0, I'm going to rewrite this like I did before. Yeah, like this. Right, now I'm going to group them like this. And I'm going to take the second grouping to the right hand side. So alright, now condition on this fact that the population mean is mu1, this must have the standard normal. Now once again, if you don't know why, let me explain. Because X bar, one of the properties from the video on the normal distribution is that X bar given mu equal to mu1 must have this distribution. This is one of the properties I mentioned, so which implies that X bar minus mu1 must be normal with 0 mean and variance. This, right? And this implies that this must have standard normal. Okay. So this is what I meant when I said that this guy here must have standard normal. Alright, so using this, you can write this as the probability that NO1 is greater than or equal to once again, I have removed the conditioning from this line to this line, right? Because the conditioning has been used to argue that this has a standard number. Right, now in the next line, here we go. I'm going to write this as 1 minus the probability that like this, yeah, and this you can write as 1 minus phi. Phi is the CDF of NO1 yeah. Right, in the next line I'm going to use a property of phi that I gave you guys. I don't know whether you remember that. One of the properties I gave you in the video of normal distribution is that you can write phi of z as 1 minus phi of minus z. This is a property I mentioned to you, you may recall. So using this property, 1 minus this can be written as phi okay. Right, so we're not far from the end yet. And we know that this guy here, is equal to beta. So now we will finish the proof if we can solve this equation for n. Alright, so this, I'm going to take the inverse function of phi both sides. So you will get z 1 minus alpha like this, right? Now this implies that I'm going to take this to the right hand side, so this implies that and finally well, it's nearly done. This implies that root of n and finally you should square both sides. The square of root of n is n, the square of this is sigma squared, squared divided by mu1 minus mu0 squared. Right, so the proof is complete. Right. Okay guys, so this completes the video on examples on one sample tests.